three hydrogen ions are here, so three hyperconjugation forms are possible. Three are possible with it. Three are possible with it. Nine hyperconjugation forms are possible. Whereas if I replace one of this methyl by hydrogen, let's say this is a secondary carbon, not a tertiary carbon, then 3 and 3, 6 hyperconjugation forms are. If I replace R2 and R3 by hydrogen, means this is a primary carbon, so it shall be very unstable because it shall have only 3 hyperconjugation. And methyl cation shall be least stable. So this is the reason primary carbon doesn't undergo SN1, they undergo SN2 because they doesn't have a issue of steric hindrance. These ions have high steric hindrance in this form. So that's why it follows this mechanism because its carbocation is stable. Tertiary carbocation is relatively stable but not highly stable. But if some such type of groups are attached, it shall be highly stable as well. So this is the reason why tertiary substrate always undergo SN1 mechanism, primary substrate always go SN2 mechanism, and secondary substrate shall undergo mixed type. It may undergo SN1 as well as SN2. Right. So proceeding further, let's say when we are having here our terminology, you would have come across classical carbocation and non-classical carbocation. This is a very important terminology, which is very important to clear at this stage because you are using these terminologies later. So you have come across carbocation. One old terminology is used called carbonium ion. Keeping in mind carbonium ion terminology doesn't exist at all. Because carbonium, whenever we say carbon and onium. So according to IUPAC nomenclature, when we are talking about onium, it means some entity is making a one bond higher than the normal. For example, if very simple example, if you have water, add acid to this. Water molecule shall be protonated. What you shall get? You shall get H3O and you write positive charge on oxygen. This is called oxonium ion. Oxonium derived from ox. Ox means oxygen. Oxonium means positive charge on oxygen. When it is making one bond higher than normal, oxygen makes two bonds. If it is making three bonds, it shall carry positive charge. So this is what we mean. When oxygen is making three bonds, carrying a positive charge, and this is called oxonium ion. Let's say nitrogen, ammonia. If we react ammonia with H positive ion with any acid, we form ammonium ion and H4 plus ion. Why we call this ammonium? Because ammonia is protonated. Nitrogen is making four bonds, one higher than the normal. So that's why this is called ammonium, right? So ammonium ion is normally this terminology is used. In fact, IUPAC is ozonium. Aza for nitrogen, azonium. When nitrogen is making one bond higher than the normal, mean making four bond with positive charge, it is called azonium. But normally this is called ammonium. So that's why relevant to NH4 class this has been associated. If you have four alkyl groups attached with nitrogen, this is called azonium, but very rarely observed. So common name is normally used. So it is called ammonium. So ammonium is common name, but azonium is its IUPAC. Very similar if you have seen the mechanism of addition of halogens to olefins. Halogen add and generate three membered ring if you remember and carries a positive charge. So halogens make one bond, but when they are making two bonds, you see we call them bromonium ion, chloronium ion, iodonium ion, ending with onium. So whenever we are using this terminology onium, it means some atom is making one bond higher than the normal. One bond higher than the normal. and carrying a positive charge. So if we say carbonium ion, it means carbon is making one bond higher than the normal. It means it is making 5 bonds. But when we are talking about this carbonium ion, we show a positive charge on carbon making 3 bonds. So this is a contradiction. That's why carbonium ion doesn't exist in our chemistry, but in mass spectrometer, the carbonium ion does exist. Carbon making 5 bond, we shall see that in next semester in spectroscopic method, especially spectrometric methods, the mass spectrometry. We shall see in mass spectrometer, carbonium ion can be generated, but in laboratory, carbonium ion doesn't be generated. We cannot have a carbon bonded with 5 atoms and having a positive charge. और भी काम करने को. So this SN1 mechanism is entirely different to SN2, and keeping in mind we use the terminology carbocation, and similarly carbonium ion terminology is no longer being used, right? So this is very important to understand. But carbocations are of two types. One is called classical, other is called non-classical carbocation. What is a classical? Let's say I have presented here. This is a classical cation. If this cation is stabilized by a pi electronic density by resonance, this is called uh, hello, hello. माइक किसका ओपन है? Asma Rouge. Who is Asma Rouge? She's supposed to switch off her mic. Is she listening? So this is a carbocation. In fact, this carbocation has two possibilities. If the cation charge is stabilized by pi electronic density, not necessarily, maybe if there's a heteroatom present suppose here, so like oxygen, maybe nitrogen, maybe any other atom, if that is generating non-bonding electron. So ultimately we shall say if any stabilization is done by pi electronic density or by non-bonding electron pair density, so that is called classical carbocation, meaning it is stabilized by resonance. But if some carbocation is not stabilized by such entity, it is stabilized in a very different way. So that is called non-classical carbocation. Just like if I show you the next slide. So just look at here. This ion, if we have a phenyl is here, methyl is here, hydrogen, and this X group leave, generate this carbocation. This carbocation is stabilized by this pi electronic density, right? So if it is stabilized by this, so this is called a classical carbocation. Let's say rather phenyl, we have a methoxy group, let's say present here, OMe. So oxygen have a non-bonding electron pair, it is stabilizing to this positive charge on this carbon due to resonance. So that shall be also a classical carbocation. A resonance stabilized carbocation is normally called classical carbocation. So, what is a non-classical carbocation? Non-classical is such ion which is not been stabilized by resonance, right? So this is a major difference. Now let's see, I am going to exemplify it. You are already familiar with classical carbocation. So the carbocation you are already familiar with undergoing stabilization by olefinic alkynic carbon system or by aromatic system. This is called classical carbocation. So what is a non-classical? Let's see, I am going to present a few examples from the literature. Let's see, we are having this bicyclic system. If you remember, this is very simple molecule. This is numbering starts from here: 1 2 3 4 5 6 7 8. This is 2 bromo uh, within the parenthesis having 2 2 2. uh, this is a bicyclic system, right? So this is a bicyclo 3 3, sorry, 2 2 2 bicyclo. So how many total carbon are there? 8. So octane. This is the structure, but this doesn't exist in this form. It exists in this form. I have presented in this is a board conformation, one board conformation, and this is, if you remember, this is called Flagstaff position. This is called Bowspot position. So the Bowspot position are linked up with each other. So this molecule exists in this form. This is the conformation I have presented. So what happens if this bromine leaves from here? What it shall generate? It shall generate a positive charge, right? So we have a hydrogen present here, and if this bromine leaves, so it shall have a positive charge. Now this positive charge is a secondary charge or secondary cation. Now let's see if sigma bond, this sigma bond transfers from here to this carbon. In fact, this carbon and this carbon is making this sigma bond. This is a sigma bond is being transferred from this carbon to that carbon. This is what we call. This is we call migration or molecular rearrangement. Anything which migrate from one to other is called migratory group. This is migratory origin and this is migratory terminus. That center where the migration starts and where it ends, that is migratory terminus. This is migratory terminus, this is migratory origin, and this is the group which is migrating from here. This is the migratory group, right? So this is the, if it transfer from this position to that position, so this is in fact called non-classical carbocation. You see, this carbocation is not stabilized by pi electronic density or non-bonding electron pair. A sigma bond is stabilizing this positive charge. Although it is generating a secondary carbocation, this secondary carbocation and this secondary carbocation have almost equal energy, but this is more stable. Why? Because it has a 6-member ring this side, 6-member ring other side. Here it has a 5-member ring on one side and a 7-member ring on the other side. So this is not that much stable. This is more stable, but it does generate this, right? So this is the one I have presented because it is not stabilized by electronic density of a aromatic system, olefinic system, alkyne system, or a non-bonding electron pair present on some heteroatom like oxygen, nitrogen, sulfur, etc. So anyhow, this is a non-classical carbocation. Now see another example. Look at here. This is the same, but what difference is here and here? I have provided a phenyl ring at this position. I attach a phenyl ring at this position. This is the difference. Otherwise, there is no difference. You see, this substrate and this substrate is same. Difference is this phenyl ring. I have fused this system with a phenyl ring system. Now, if this bromine leaves with electron pair like this, generating a positive charge here, so it is undergoing SN1 mechanism. Look at here, this is a secondary carbon. It is not undergoing such type of substitution in fact. Now, if same migration starts from here to there, you see, it is generating a positive charge here. But now this positive charge is stabilized by resonance. Here, this carbocation was more stable than this one. So look at here. Now here, this is not stable. This one is more stable because this is stabilized by resonance. But it is stabilized by resonance as a result of this sign because this is been isolated. This is been isolated when we react this molecule with, let's say, a good nucleophile shall instantly react with it. So it shall react this bond with this next to phenyl ring. Nucleophile shall bond. It is not going to bond at this position. If it is bonding here, it means it is SN2 reaction is going on. Or this is less stable, this is more stable right now. It was opposite in this case. But both of these are non-classical carbocation. This is a non-classical carbocation. This is a non-classical carbocation because this is being stabilized by a sigma electron pair. This is stabilized by a sigma electron pair, not by pi electron pair. These are called non-classical carbocation. So hopefully you are familiarizing the difference between a classical and a non-classical carbocation. Let's see, just to quote a few more examples in this case. We have a cyclopropane ring, three-membered ring bonded with this X. X is a good living group, maybe any. You shall see that in the factors affecting the reaction, these nucleophilic reactions. We shall see that later in next lecture. But if this X is leaving, X means good living group. If it leaves, it shall generate a positive charge here that I have presented here. What sort of carbocation? This is a primary carbocation. See, this is primary. Attached, this carbon where positive charge is generated is attached to only one carbon. So this is the, in fact, the difference. Now what we can further perform in this case, this sigma bond is transferring to this carbon. You see, this one or that one, which are identical. So both of these two are identical. The sigma bond is transferring to this carbon. When it is transferring to this, you see one ring is being extended. This carbon 1, 2, 3, 4. Positive charge shall be on this carbon, this one. You see, three-membered ring is being converted into a four-membered ring. So here there is a more angle strain. You have come across in previous semester in organic chemistry course about Bayer strain theory. So more angle like this, more shall be the instability. More angle strain is in three-membered ring. Ideally, it should be sp3 hybridized. Ideal angle is tetrahedral angle, which is 109.47 degree. But you see, what is the practical angle here? The angle between these two carbon is 60 degree. If it is 60 degree versus 109, there is a huge difference. It is a 49.47 degree difference. It is strained. So this is a reason three-membered rings are unstable and this is more stable. One, this is primary carbocation. Second, this is secondary carbocation. Similarly, this is more strained, this is less strained. So this carbocation is much more stable than this primary carbocation. So that's why this cation is stabilized by sigma bond electron pair. So that's why this is also a non-classical carbocation. Now look at the other. Look at this substrate. This is the substrate that we call OTS. This oxygen bonded, this whole group is called tosyl. We shall see that in next lecture why it is called tosyl group, etc. So this is a good living group. This electron pair transfers on this oxygen, and as a result, positive charge is generated at this position. If positive charge is generated at here, this is a secondary carbocation, right? Now look at here. If this sigma bond transfer if the sigma bond transfer from this position to that carbon, right? It is this bond is transferred here. You see, this carbon making a bond with this, not with this. So this carbon becomes positively charged. This is a secondary carbocation as well. So look at here. If this OTS is not present here, it is present on other carbon, and the pi bond is here. So in this case, this OTS is leaving and this pi electronic density is transferring. So both of these are generating same cation. You see, this electron has been transferred from here to there, right? So if it is pi electrons are being transferred basically from here to there, so this is generating a double bond at this position, right? Positive charge here. Then again the positive charge shall be balanced with this to generate the same cation. So it is generating the same red, non-classical carbocation either by this protocol or that protocol. Here sigma electrons are transferred here, although pi electrons are involved, but this is still called non-classical. In bicyclic or polycyclic system, it is called non-classical carbocation. Now let's see. I'm just going to present another example. This chlorine is present at this position. If it leaves, so we shall get a positive charge here. This positive charge is stabilized by this pi electronic density. There are two possibilities. This carbon may be making a bond, which is a very long bond. This carbon may be making a bond with it. So I have presented these two bonds. If this carbon make a bond with it, we shall get a positive charge here. If this carbon make a bond, we shall get a positive charge there. Or look at here, in all cases, if this bonds or that bond, we shall get a secondary carbocation. But if this Cl leaves here, positive charge shall be here, it is a tertiary carbocation. This ion shall be more stable as compared with this. So this is stabilized. This is also non-classical carbocation, which is less stable here, but this is more stable. So these are just to, I have tried to explain the difference between a classical and a non-classical carbocations. So you should be replacing, calling the carbon positively charged entities as a carbonium ion. Carbonium ion, keeping in mind, doesn't exist. It is the carbocation, not carbonium, right? So this is all about this lecture. So we shall focus on the third type of mechanism, SNI mechanism, which stands for substitution nucleophilic intramolecular. All right. So what I have suggested you the chapter in aliphatic substitution reaction in the Clayton's book. Just go through that. You shall find very interesting cases in that case. So before we meet tomorrow, so just read that suggested readings. I hope you have already studied, but you have studied SN2 reaction. Don't study the SN1 reaction as well. So afterwards, we shall focus on SNI mechanism. So if there are any questions, the session is open. If there is any questions.
Yes, sir, I have a question.
What is
Excuse me,
your
sir.
question?
सर ये जो आपने लास्ट रिएक्शन आपने बताया है, प्लीज़ आप उसको रिपीट कर दें, जिसमें आपने पाई इलेक्ट्रॉन की ट्रांसफरेंस बताई है तो साइल क्लोराइड वाला, आप उसको दोबारा बता दें कि वो कौन से वाला है, लाइक ये नॉन क्लासिकल है या क्लासिकल है?
Which one?
सर इन द लास्ट स्लाइड you have just discussed right now.
Which one?
Yes, sir. In this one, the conversion of structure number 2 into 3, that is pi electron pair transference.
Haan ji.
So can you please tell me that this is classical or non-classical carbocations?
It involves pi electron transfer, but pi electron transfer, the pi orbital are not parallel to each other. You have seen already here when we are doing this pi orbital and this pi orbital, if they are parallel to each other, then they shall undergo sharing of pi electrons, right? Let's say this pi
Yes, sir.
orbital is along the plane of this board, but as this phenyl ring is presented in this pi orbital is perpendicular here. So when two pi orbital are perpendicular, they shall not overlap. So this phenyl, if rotate 90-degree from here, then the pi orbital present here and this pi orbital shall be parallel to each other. Then they can show this pi electronic density, making a double bond there. So here pi orbital present on this conjugated system and this pi orbital present on this tertiary carbocation. These, if present in such a form, then they are going to stabilize the charge. But if you are comparing this bicyclic system, in bicyclic system, this pi orbital, or let's say pi orbital, if I present this pi orbital, and this positive charge here, they are not in same. No, they cannot rotate, if you remember, because this rotation is rigid. This pi orbital have no carbon-carbon free rotation. But in previous example, if you see here, this carbon and that carbon, they have a free rotation, single bond. So this
Yes, sir.
phenyl ring can rotate in any direction to acquire the pi orbital of that parallel to this. This is only possible if it is in this form. This phenyl ring rotates 90-degree, then its pi orbital and this pi orbital shall be parallel to each other. Because pi bond is always formed by parallel overlap. So for this is what we call resonance stabilization. This is we call classical carbocation. But here, although pi electrons are involved, but it is no
Yes, sir.
longer being pi orbital is not parallel to this plane. This is why we are calling this non-classical. It is not a parallel overlap because this carbon have no possibility of rotation. It is a rigid structure in fact.
Yes, sir.
Yeah,
एंड सर
that's
ये जो आपने लास्ट क्लोरीन के रिमूवल वाला जो रिएक्शन बताया ये भी प्लीज एक दफा बता दें, इसमें टर्शरी कार्बोकेटाइन कौन सा है और दूसरा कौन
exactly.
सा वाला है?
Let's say this carbon leaves from here. So this carbon which is present shall be straight. We shall have a pi orbital like this. Pi orbital shall be like this, right? And look at
Yes,
pi
sir.
orbital here. This pi orbital is alive. This one. This pi orbital is alive. This one. So
Yes, sir.
this pi orbital and this pi orbital, they are perpendicular to each other. But even then,
Yes,
if
sir.
they are stabilizing each other, this is we call non-classical.
Okay.